This is from last lecture. Okay, this is today's lecture. Can you see my slide?
Yeah.
Okay, so we already gave the overview and the linear algebra. So today I'm going to focus on the basics of quantum mechanics, but in the context of quantum information and see how it works. I hope by the end of this lecture, you will realize that you don't really need much of quantum mechanics as long as you know the basic 3 rule that I give you. So by using the qubit, I will illustrate these rules. So now we'll talk about the so-called mixed state later, and maybe introduce you some really simple quantum algorithm. Okay, as always, interrupt me if you have any question, or type your question into the chat. So I'm giving you really some rough history of the development. I think it started really in the early beginning of quantum mechanics from Einstein and coworker. And then you can see there's some gap, but in the 60s, John Bell entered the discussion related to Einstein, Podolsky, and Rosen. They questioned whether quantum mechanics is complete. And he proposed some inequality that can be used to test whether the classical theory is correct or whether the quantum mechanics is correct. And there are some improved inequality, and then came with an experiment that actually verified that the classical way of thinking of the phenomenon is not correct. We should use quantum mechanics. So that's really the early beginning. And then later, people start to think about, quantum mechanics, maybe it can be used to do something useful. In the context, you can actually use quantum mechanics to send a secret key. You can establish a random bit string among each other and then use that to send information. And this is more about communication. And later, a few people, including Daniel Manning, Feynman, they proposed using quantum mechanics for computation. So there's some idea of quantum computation start to emerge. Around the same time, Ecker actually proposed a different communication scheme using entangled pairs. So we're going to define what entanglement is and give you example of entangled states. And from there on, there are a lot of research development. For example, quantum teleportations and dense coding, etc. The ultimate success, or maybe the most important development, is the Shor's quantum algorithm, which actually demonstrates that quantum mechanics actually can be used to do something much better than classical theory, classical rule. And you might have heard from the news that Google last year has demonstrated something they call quantum supremacy, meaning that they have been able to work on, for example, large number of qubits, 53 qubits, and they demonstrate something that cannot be efficiently simulated using classical computer. So this is really a rough history, and a lot of important development also were not mentioned, but I think this served the purpose of the early history of quantum information. Okay, but maybe some of the words that I mentioned here, you have no idea, but during this course, you will learn more detail, and then probably when we learn a few of these topics, you can come back into the list and you will see how amazing the field evolved. So the most basic things is called quantum bit. We call it qubit for short. Everybody knows a classical bit, right? It's 0 and 1. So classical, we just say classical will be 0 or 1. And so there are two distinct states, and that's it. But for quantum mechanics, the state lives in a space. We call it Hilbert space. Sometimes we denote by C2, C meaning that the coefficient can be complex, 2 meaning that there are two components. But this is just mathematical notation. We usually give a label to a quantum state or qubit state, psi. And you can imagine this is a vector. So instead of just 0 or 1, you can be in a superposition of alpha times 0 and beta times 1. So this looks like a vector. So usually we write it as this. So psi is like a vector, has two components for a quantum quantum bit state. So this is a pure state, okay? Okay, so I want to mention that we usually require this convention that this is defined to be that it's normalized to 1. So what this means is this vector has length 1. The motivation is about probability. So you can regard that the norm square of each component is actually a distribution. So it has this probability of being 0. It has this probability of being 1. So you can interpret that way. But we'll come back to that later when we talk about measurement. Okay. So this is really simple equation, right? Just a component, a vector. And we say that it's normalized to 1. So this is where linear algebra comes in. So I'm going to use the Dirac bracket notation. But if when you are confused, you can always return to the vector notation. So I'm going to say that this is normalized, meaning that the V has norm equal to 1 or its square is 1. So to calculate its square, I just take the V and dot it is Hermitian conjugate vector, right? We just start that. In terms of bracket, you can write this way. It's a row vector dot into a column vector dot into a row vector with a dot, just to signify that this is a inner product. But usually we simply drop that. We just write in this more compact notation with the two sides on the left of a bar and between the angular bracket. But the mathematics or the algebra is simply just taking this row vector multiplied by this column vector and become just a number, right? So this is really simple calculations, and that's 1. So this is the normalization of a wave function. Sometimes we also call this a quantum state or a wave function. Okay. Yeah, so this is a two-component vector. So we can always expand the two-component vector in terms of its component, right? So in order to do that, I need to define a basis. So I would take, the most natural is take 1, 0, and 0, 1 as the two vectors that would be used for as a basis, right? So, and we sometimes denote this as an up, an arrow pointing up, or we also use 0 for this 1, 0 vector. And for the 0, 1 vector, we use the notation down in the kit notation, or we use 1. So you'll see these notation being used interchangeably in many places. So I'm going to introduce these right in the beginning, okay? So what this means is that psi the state psi here can be just written as alpha times the up state plus beta times the down state. Yeah, this is really trivial, right? So it's really just like this. Okay. Looks like I'm in the pen mode. Pointer. Okay. Okay, so, but we can ask, this basically define the state, and then we can ask how does it change? And you know the classical bit can be flipped, right? You have a classical gate called NOT, or sometimes we call it X gate, which basically flip 0 to 1 and vice versa. So in terms of a matrix that act on a vector, you can write this NOT gate as a 2 by 2 matrix 0, 1, 1, 0. And it would flip, right? So X acting on the up state is simply just this matrix applied to the 1, 0 vector. You can verify easily that this becomes 0, 1, so it becomes a down state. Okay, so this is the action also you have in classical logic. Okay.
So for the 0, 1, 1, 0 notation, do we just choose any basis?
Do we already choose the basis? Right. We just define this 0 as 1, 0, 1 as 0, 1.
Yeah, but to write in component notation, you need a basis first, right? So you just choose a basis.
Yeah, you choose some basis.
Okay.
Yeah, this could be, right. And in terms of the vector, you could write the 1, 0 vector. The first one may be representing in the X direction. The other one is Y direction. Or you could choose, this could be a north, and then this could be a east, something like that. Okay.
Okay.
Okay. So, yeah, so I already introduced the notation bracket. So we usually call this as a cat. And the broad notation is basically the Hermitian conjugate of that. So it's going from the column vector to a row vector. Okay. Yeah, so as I mentioned, the inner product give you a number, right? So this is what we just did. And we normalize that to 1. So you learn inner product in the algebra, but there's also outer product. And then this would, if you take the outer product, meaning that instead of taking row times column, you take column times row, it becomes a matrix. So alpha times alpha star become alpha absolute value square, and this alpha times beta conjugate, etc. So we can use also the bracket notation. You write kit first, and then the broad notation followed by that. Okay. So we sometimes call this as row. This row, we call it a density matrix. Let's see if I can switch to the pen mode. Yeah, we call it density matrix because this is a matrix. Density in the sense that it represents some kind of probability. As you see, this diagonal element, alpha square and beta square, they represent the probability, the diagonal, just right. Diagonal element represent probability distribution. Okay, it representing the probability that the state may reside in the 0 component and reside in the 1 component. Okay. Yeah. So the trace in terms of the matrix theory that you learned, the trace of a matrix, okay, just by notation, I write trace row of this by notation, definition. And I write by definition, this is the column vector, that's row vector. And you'll know that the trace A and B is equal to trace BA, right? You can just swap them. And that end up with the previous normalization. Okay, if you use that, you directly go to this. Okay, but I didn't do that in this step. Okay, so I basically multiply them. This is multiply. I then get this matrix, and I use the trace is the sum of the diagonal. So this use sum of diagonal. But here I could actually go from here directly to this by using the cyclic property. Okay. So yeah, I'm just reviewing some of the linear algebra. Okay. Yeah, yeah, that already mentioned. So the trace of outer product is actually the same as inner product. So this is what you have from the linear algebra, right? So, but in terms of quantum mechanics, this is meaning that the normalization is 1, meaning that if you sum over all the probability distribution, right? This is sum over probability at 0 plus probability at 1, it should be 1. It should be normalized. That's why we, whenever we can, we normalize the wave function. Okay, and you can see that what I said earlier, right? The density matrix, the diagonal element represent probability distribution. Okay, when you may ask, what about the off diagonal element? Let me just comment the off diagonal element represent coherence. Okay, it will become clear later, but let me just mention here. If it's 0, that means there's no coherence between 0 and 1. And you've seen this last time in terms of interference. If you don't have the cross turn, you don't see fringes. This is where fringes come from. Let me just put fringes here. Okay. Yeah, it's not easy to write. So that's why I prepared the slide first, as at least most of the content that I want to mention is already on the slide. Okay. Any questions so far? No? Okay, I'll move on. Yep.
What is the coherence and fringes?
Can you say it louder?
What is the coherence and fringes?
Okay, were you here last lecture?
Yes.
Okay, so let me go back to previous one. Remember we have this, right? We have this, if you have a label, then they're orthogonal and there's no fringes. Let me just use the slideshow mode. But when we remove that, we will see fringes. And then I had a formula that says this, right? So, and when I take the absolute value square of this wave function, I see the cross term, right? This is like psi 1, psi 2. This is like alpha, star, and beta. So this gives you the coherence and it's related to the fringes that you have, okay? If somehow this is 0 because of this becomes 0, that means this is 0, okay? So that's what I can explain for now. But we will come back to this later on. Let me just keep this. Does that answer your question? Okay, maybe you can review this part of the video later, but we will come back to that. Yeah, this is a very important question. Okay, so we introduced the qubit state, right? The qubit wave function, and we use this parametrization. We say alpha and beta that are the two components, but because they normalize to 1, so we can choose a specialized way of representing these two complex numbers because they normalize like this. So we can write alpha as a cosine of certain angle. So I just specific put theta over 2 here. And beta, I can write as sine theta over 2, but because it's complex, I can always add a phase, e to the I phi. You may wonder why I don't put a phase in alpha. Well, because I can just shift that phase to beta. So overall, phase is not that important, okay? So why do I want to do this? I want to go through the density matrix again. So I have this density matrix is basically the column vector times the row vector, and I obtain this 2 by 2 matrix, right? If I use the specific parametrization here, then I can just plug in, and notice that I use the trigonometry equality. I write this as 1 plus cosine theta over 2, and the cross term alpha times beta has the sine cosine, which is actually sine over 2, right? Twice the angle. And I still have this phase, and this is just the conjugate of this term, okay? And this one is sine squared, so I can just rewrite this. So you may wonder why I want to do this. You will see that later, because if we define the coordinate, this is like a spherical coordinate, right? Rz is the cosine theta, Rx is the sine theta times cosine phi, Ry is sine theta times sine phi. This is like a unit sphere. Then I can write this density matrix in this way, right? So there's 1/2, so that's 1 here. So I pull out 1/2 factor, this one here, and this Rz here, right? Because this is cosine theta. Rx comes from here, and Ry comes from the imaginary part, right? So I have this matrix, but I want to actually separate it into 4 different parts. One is the diagonal element, 1, 1. That has nothing to do with the Rx, Ry, Rz. The second term is 1 that has coefficient Rx. And there's a matrix followed by that. And those are Y. And you see that there's an imaginary part, right? Minus I and I here. The third one is Rz. The matrix is different from this one, and this is identity by a minus sign in the second diagonal element. Okay. Okay, then this is just for simplification for those who like to compactify notation. Okay, this is identity, this is X, Y, Z. We can just say that this is half identity plus a vector times a vector of matrices. So the vector of matrices. So when I say R dot sigma, I basically mean Rx, sigma X, Y, sigma Y, RZ, sigma Z. And notation is that sometimes people write sigma X as X, sigma Y as Y, sigma Z as Z. Okay. But there is a vector R. So what is this vector? This vector is represented by the three component, right? So you can imagine there is a sphere, unit sphere, pointing in some direction with theta angle with respect to the z-axis, and also phi in the xy plane measured from the x direction, right? So this is usually called Bloch sphere. Okay, so mentioned in the title. Yeah, and the three matrices are called polymatrices, and it's defined as these three matrices here. Okay. Any questions so far? This is probably our first derivation. So in some sense, a qubit state, you can view it as a vector, two component vector, right? Alpha and beta. But you can also regard that as a vector pointing in some sphere. So everything here is real. In this Bloch sphere picture, these component of the vector is real, right? So this is a real vector, but this is a complex vector. In physics, sometimes we call it spinor, but it's not that important if you haven't heard that before. But if you desire to use a real coordinate, this is the Bloch sphere that give you a real three-dimensional coordinate, right? So we start with a wave function, which is a pure state. It's represented by a vector on this unit sphere. Okay. So, and we notice that this length of that vector is 1 for pure state. Okay. So I want to talk about property of these matrices, polymatrices. They are really special matrices and has an important role in quantum mechanics. Yeah, they square to identity, right? If you take, okay, this is easy to see if z square is really identity. X square, you can easily calculate this, right? So this is 1, and the cross term here is 0. So they square to identity. And they anti-commute. So I use this symbol to represent x plus y plus x times y plus y times x. They actually add up to 0. You can verify yourself, or maybe let's just do x and z. Okay, so you get 0 minus 1, 1, 0. And when you do the zx, you actually get the opposite. So they add up to 0. So we call this anti-commuting because x, if I swap the location, the order of the two matrices, it get a minus sign. Okay. And there's also interesting property that if you define this this co-commutator, this is just a name, but it's defined by xy minus yx. It turns out y minus yx equal to I times z, and yz commutator is ix. So it has these symmetry there, so in a cyclic way. So this is just mathematical property of these matrices. But in terms of physics, in quantum mechanics, these are related to rotation. So rotation, you have, for example, z, you rotate some angle. They're actually related to the so-called spin angular momentum operator. If you haven't heard of this, it's not important in that sense, but what it means, it's an action. So maybe more importantly is that these representing actions on a qubit. And the physical meaning is rotation. Okay. So, for example, if you want to rotate in the Z direction, let me bring up the pointer. Yeah, rotation around Z with angle phi, that's represent the action of rotation. And this will be representing the action rotation around the y-axis by an angle phi. So notice that there's a factor of 2. So if you're a physicist, you know that these Pauli matrices over 2 and times h bar is the spin angular momentum operator. Okay, in general, rotation around any axis n, so let's say n here, rotation around any axis by angle phi is represented by that vector dot sigma dot the vector of Pauli matrices, right? I introduced this notation earlier. You can actually use, remember we use some kind of Euler formula, e to the I theta equal to cosine theta times I times sine theta. This is a corresponding formula. So that's a corresponding formula with matrix. Let me say Pauli matrices. Okay, so you can really write this instead of in the exponent, you can bring it down. So cosine phi over 2 times identity minus I sine phi over 2 times the inner product of the vector times the vector of the matrices. So we call that this here. Right, R dot sigma is really just Rx sigma X, Ry sigma Y, Rz sigma Z. Okay. So far, I'm reviewing the mathematical property of Pauli matrices and its physical meaning. Yeah, so I already mentioned that. So they represented rotation. So sorry that this is blocked by the annotation, but what it says here is the X, Y, Z are themselves rotation by 180 degree. For example, 180 degree is pi over 2. Sorry, 180 degree is pi. But this is e to the I pi z over 2. And if you use that formula, it's 0 minus I pi over 2 z. So it's minus I times z because sine pi over 2 is 1. So these Pauli matrices themselves are rotation by 180 degree. Okay, so this is also the reason that X flip up to down. Right, so X, for example, X is a rotation around X axis by 180 degrees, so X flip up vector to down. Okay. And these matrices, they are Hermitian, right? If you take the Hermitian conjugation, you transpose and take complex conjugation, X equal to X dagger, Y equal to Y dagger, Z equal to Z dagger. And they are traceless, meaning that you sum over the diagonal, they are 0. Okay. I believe half of you probably know this. Physicists should have known this, but if you haven't seen this before, this is just mathematical property and the physical meaning. You can always come back and refer to this table of formula. Okay.
Question.
Yes.
Can come back. You could go back to the commutator
Yeah.
part. I think
Right.
the commutator of x, y, and other things should be normalized and different. I mean, like the commutator of x and y should be, I think, 2iz or something.
Oh yeah, yeah. You're right. So it should be 2. Yeah, there should be a 2. It should be a 2 factor. Yeah, thanks. Because in terms of, if you're a physicist, in terms of angular momentum, this is I epsilon x, y, z, s, z, but s is actually sigma over 2. Yeah, there's a factor of 2. Yeah, thanks for that.
No problem.
But you can verify this by yourself that what is important is the commutator x, y goes to z. Yeah. Okay, so somehow we have a pure state, but we go through the derivation to get the density matrix, and we found that there's a constraint, right? So this is normalized to 1 for the vector. In another way, if you take rho square, because it's rho is like this, right? But this is where the Dirac notation is useful. I can combine this first and I get 1. So I'm left with this itself. So this is rho. And if I take trace rho squared, because it's the same as trace rho, it's 1. So this is sometimes referred to as purity. If purity is 1, that means it's pure state, okay? Purity 1, pure state. Okay, you may ask, okay, we've been seeing only the vector with length 1. I haven't seen any mixed state. But in general, if I write the general formula for this expansion, right? If I take the square, you can do the algebra yourself. This is 2 times the cross term times the r square term. So yeah, there is maybe some formula that this actually is this times identity. If you take the trace of the rho square, you see that it's 1 plus r squared over 2. If r is less than 1, then this total number of the trace would be less than 1. So that's the case of a mixed state. So meaning rho squared more than 1 for mixed state. And mixed states are those states that I cannot write as a kit times bra. It need to have at least 2. Okay. Yeah, so this means that pure state in terms of certain basis, it can always, so pure state in terms of basis, rho can always be written as this, but mixed state would be in some basis. Would be like P and 1 minus P. Okay. We come back to mixed state later. So if you don't really fully grasp the notion, it's fine. But I'd like to invite you for questions. No? Okay. Maybe just to illustrate, how do we get mixed state? We can just mix, so in terms the name mixed state, you can just by mixing pure state. Okay, we call that, I have this Bloch sphere representation of a pure state. So I pointing up and down. And I mentioned earlier, if you regard that in certain basis, you will get eigenvalue P1, P2, which is actually what I wrote here. This is P1, this is P2. If you diagonalize a 2x2 matrix, you will get 2 eigenvalues, right? So let me represent that as P1, P2, and 2 eigenvectors as psi1 and psi2. In fact, it's, if you choose the right basis, this is psi1 and this is psi2, okay? And the P1 and P2 representing the weight, how you mix them together. So how you mix them together is by mixing the density matrix for the pure state 1 with probability P1, and the one for psi2 with probability P2. Okay. So this means that the mixed state comes from a statistical mixture of a pure state. So imagine there's a source, maybe a source, and with probability P1, the source emits psi1. With probability P2, it emits psi2. So you can then understand the source as a mixed state. Okay. This is just mathematics. So because these are eigenstate, the way I'm writing is in terms of eigenstate, so they are orthonormal. So meaning their inner product is 0 if the two are different. If you use psi1 and psi2. I want to just mention that in general, there are infinite number of ways to decompose a mixed state. Just like you can take another arrow, an arrow, etc. If you weigh them properly, you will end up with certain average arrow, and that average arrow may have a different way of decomposing. Okay. Okay. This I'm giving most of the mixed state. This may be a bit more than I needed in today's lecture, but I just tell it in front. So, any question? Okay. So if you don't understand the mixed state, that's fine. At least we're going to give you the basic rule of quantum mechanics, and then we're going to illustrate a really simple quantum algorithm, if I have time. Okay. So the basic rule of quantum mechanics first is superposition, right? So you've seen that. So it could be like double slit, go to here. This will be a superposition. Okay, yeah. And in terms of qubit, it means that this qubit psi is in a superposition of up and down. Okay, that's really just what it means in terms of, let's say, a quantum coin representing the face of Einstein and the back. If you have a such coin which is quantum mechanical, you can put it in a superposition. Okay. So that the superposition is really simple idea that you also have in classical wave. But you can ask the question, how do you put a coin of Einstein in such a superposition? Let me just give you an example. Suppose this is up, representing the phase of Einstein. If I have a gate, I mentioned the gate, X gate before. If you use X gate, it would flip the front to the bottom, front to the back. But I want to do something maybe slightly different. I can take this matrix. This matrix would flip the up state to a superposition. So let me just apply, this really just applying the up is this vector, and I just apply that 1 times 1, 0 is 1. 1 minus 1 times that is 1. So this really put it in a superposition of up plus down. Okay, so let me just erase that. And then you would ask the question, how can you get these quantum states? So the idea is that you would use some kind of evolution. This evolution is a driving force of the system. So that's the next rule. So first, let me just remind you, the first rule is superposition. The second rule is just to illustrate how we get, for example, a Hadamard gate. It's through the evolution, and this evolution should be linear and unitary. So let me come back to this later. So let me introduce unitary first. So unitary meaning that the matrix that I write before, for example, Hadamard gate, is unitary. It satisfies its dagger times a cell equal to a cell times dagger equal to identity. You can verify that that's the case. Linear meaning that when I have a superposition of a quantum state, and this quantum state is acted by a unitary gate, I can actually do this in a different order. I first apply U to the first component and apply U to the second component, and I add them together. Okay. Let me come back here. If you learned quantum physics before, you will know that the system evolved under certain equation called Schrodinger equation. So we won't be solving this in this course. So at least not the moment. So it satisfies this differential equation. And there is a formal solution, is this. And by seeing this, you identify a gate. So this is the gate, right? You don't need to worry about how we get this from there. Just need to verify. Maybe we can just verify. You take the derivative of this with t. The only t dependence is here, so you just take dt on this. You really just get pull down I h bar h and then this. Okay. Then you can verify. Okay, if you put back the side 0 into here, and side 0 into here, you can identify your cell. This is actually psi of t. Therefore, you verify this equation. Okay. Now, any question? I'm reviewing the basic quantum mechanics, but even here, you don't really need to know how to solve this. You don't need to know. As long as you can say there is a solution that looks like that. Okay. Okay. Here I have a bit of conflict of notation. This is Hadamard gate, but this is called Hamiltonian. So I use a hat just to distinguish that. H is Hamiltonian. Okay. The third rule is measurement. So we talk about superposition, unitary evolution. You can think of Hadamard gate, X gate as an example. The third rule is measurement. So measurement, according to quantum mechanics, is it projects the wave function. Okay, what that means is, imagine you have a coin that's in a superposition, right? Alpha up plus beta down. And when we measure, usually we need to specify how we measure or what the basis of measurement. Let's say we measure along these up and down. So up here and down here. Along this basis, what we will get is that we will not always get the same outcome. We will get randomly and the outcome that can appear is up or down. So with some probability. So sometimes it's up. And here we can give a score of +1 if it's up. And when it's down, we can also give a score of -1. And how often they appear is according to this so-called Born rule. The probability of measurement in getting up outcome is proportional to the coefficient square here. So alpha absolute value square is the probability distribution of being up. And P down is proportional to norm beta square. And you can give a score. So I just represent it by a notation. Sigma z has a score +1. Sigma z has a score -1 for the down case. Right. So remember, this is alpha and beta that I also mentioned in terms of density matrix. Right. So this is actually related. So this is the rule of measurement. So in terms of more standard quantum mechanics, you would call measurement in terms of some observable. Actually, in this case, the observable is Z, poly Z matrix. And you get probability up and down respectively, and you have score, right? The score is what you get in terms of the value of measurement. And the up-down is the basis of measurement, up-down. You could also measure in the plus and minus basis. So this, in a compact way, can be written as this observable as a matrix is actually the score of +1 times is one of the component of the axis. It's up, but right in terms of matrix form. And the score -1 in terms of down, density matrix. Okay. So if you look at observable here, if you can decompose or diagonalize that, this is what you get. So this is actually when you diagonalize. And you see the +1 is the score, -1 is +1 the score for up, -1 the score for down. And you can also ask, what is the average score of measurement? So average score, according to this, right, I have probability of up, and sigma z is +1, and probability down, -1. So average score is this. This is alpha square minus beta square. Okay. In fact, this can be written as actually a matrix times a vector, column vector, and then you take another row vector to get a number. So yeah, so let me just recap. So you diagonalize the observable that's given to you that specify how you're going to do the measurement. The eigenvalues are the score and what you read out. The eigenstate up and down are the basis. Yeah. And the second part of the measurement hypothesis is that when you perform the measurement, the state that start with alpha up plus beta down, after the measurement, is randomly projected to up. So meaning that when you perform the measurement, it just collapse to up with probability alpha square. And when it collapse to up, when you measure again, it will still be up. Okay. But when it could also be collapsed to down, and when you know it's down and you keep measuring that, you still would get down. Okay, so that's the 3 rule of quantum mechanics. Question?
Why is it called strong measurement?
Can you say it louder?
Why is it called strong measurement?
Strong because it projects. It really just changed the state dramatically. There's some kind of weak measurement, you change it slightly. It does not really project, it changes slightly. Yeah, that's why it's called strong measurement.
Okay.
But this is what you usually learn in quantum mechanics. Okay, I think this is time to do some polls. So we learned the 3 rules: superposition, unitary, measurement. So I want to ask you to review a little bit and see which one you are comfortable, which one you are not. I think most people are comfortable with superposition, unitary, and large fraction of people feel that measurement is the most weird. Of course, if you have learned this before, it seems natural to you. So let me end the poll and share the results. Yeah, superposition, you already have that in classical world. Unitary, you also may have that, like rotation is a special kind of unitary rotation. Measurement is really strange because in quantum mechanics, when you measure, you perturb, you change the state. But in classical world, when you measure, you just look, and the thing that's been observed is still in its initial state. It does not change. Okay. Yeah, so let me just superposition. In fact, it actually is automatically included in the unitary. So as long as you know the unitary, that should be fine. So you could, if you want to reduce it to 2 rules as unitary and measurement, right? So because unitary take a quantum state, this can take a state into a superposition. Okay. So therefore you can just concentrate for the moment, unitary measurement. Okay. I think, yeah, so we only have 1 qubit, then we cannot do much. But if you go beyond 1 qubit, you have something weird called entanglement. So my opinion is that the true quantumness comes when you have 2 qubit or more. Let me just comment that this notion of entanglement is coined by Schrödinger. So let's take an example. So this is where the mathematic tensor product or direct Kronecker product comes in. So you have 2 qubit. I can write as up. Using Dirac notation, I can sometimes also omit the tensor product. So I write as up, down, up, and down. And these are states that looks separable, meaning that you can write as A times B, but they are states that you cannot write as a product form. For example, these are the, for example, if you write up plus down, you cannot write this, you can never write as A times B. So mathematically, this define entanglement. So this define a state being entangled, meaning that you cannot write as a separable form. And we'll see later that they're very useful. And if you have more qubit, you would need to write more if you want to use the vector notation, because the tensor product will give you more component. If you have n, like I can just write this, but in turn to represent this, it's a component vector. So using the vector would become less and less useful. So Dirac notation would be a useful way. Okay, so I want to give you an example of really the simplest quantum circuit. Actually, we already gave you one. This may be slightly more. So we have this x acting on up, become down. Okay, I'm giving you probably the simplest non-trivial quantum circuit you can have. But I want to introduce a CNOT gate. You can imagine it come from some unitary evolution. So unitary evolution, e to the minus I ht. Okay, but this is really the detailed implementation from physics. But imagine you already achieved that. You have a control NOT gate. In terms of vector, it's acting on 4 component because acting on 2 qubits state. But the physical meaning is that if the first qubit is up, represented by this projector, you do nothing, meaning that you do identity operation. If the first qubit is down, you do X, you basically flip. So this is really clear in terms of partitioning the 4x4 matrix into 2x2 blocks. The first block, meaning representing the first bit being up, it does identity. And the second block means that if it's down, then I do the X gate. Okay. Then I can imagine I start with up state. I perform the Hadamard gate on the first qubit. It brings it into a superposition. This factor is just normalization. For the moment, you can just ignore that. And then when we apply the CNOT gate, when this is up, I do nothing on the second, so it still is up. When this is down, I would apply X gate to flip from up to down, okay? From here, you get an entangled state, right? This is the entangled state, one of these. Okay. So yeah, in terms of the circuit, I want to introduce that. So 0 is sometimes we call it up, right? First, you apply a Hadamard gate, and then you apply the CNOT gate. And this, what comes out here is this state. Okay. Question? Okay. This is really just applying the 3 rule we have, but in fact, there's only this is the quantum gate take you in a superposition, and then this quantum gate is flip condition on the first bit. It also does some kind of superposition, and we have not talked about measurement. So, but let's say if I perform measurement on 1 and 2 in the up-down basis, there are only 2 possible outcomes. You can only get up, right? And or down. And the probability of getting this, remember, is according to the alpha and beta, that's the coefficient square is 1/2. This one is also 1/2, right? So maybe next time I can illustrate using the quantum circuit from the kids kit and then demonstrate the circuit. Okay, so yeah, so maybe we have some mathematics in this lecture. So even I want to stress, even if you have never learned quantum mechanics before, you can still learn quantum formation and quantum computation, provided you know the matrices and vectors. Basically, linear algebra is the underlying rule. And additionally, you need to remember the 3 rules of quantum mechanics. But it's all can be stripped down to 2 rules. Okay, so I think we're ready for the first quantum algorithm. We're using the remaining 10 minutes. So I want to pause to see if you have questions. Or let me see if there's any poll that I can do. Okay, maybe we do that later. If there's no question, we go to the first quantum algorithm. If you can go through this algorithm, have at least a comfortable understanding by really applying the rule, then you will be ready. I mean, you will be really ready for the upcoming material. So, but I would remind you the rule of what we use. But the setup is the following. Suppose there is a function f that map a bit 0 and 1 to also 0 and 1. And there are 4 possibilities, right? You know, you could map 0 to 0, 1 to 0 as well, or you could map 0 to 1, 1 to 1. And I can classify these 4 mappings into 2 types, 2 categories. I call the first type constant because whatever you map is always the same, right? They're always the same value, right? It's either 0, 0, 1, 1. And the other type is called balance because there's equal number of 0 and equal number of 1. And suppose I have a circuit, assuming there's a black box, it's doing the following action. It takes the input x, and keep it as x, but when you have a b here, it evaluates f of x and then add that to b, and then that's the resulting. So suppose this is the unitary. This is the unitary you have. Assuming this is just a rule, right? You can just regard the 3 rule is the game rule for quantum mechanics. So the question is the function balanced or constant? Suppose you are given this action without telling you what this unitary is doing, but you can operate that on your quantum state. Well, mathematically, this is equivalent to ask whether the f of 0 value plus f of 1, the binary addition, right? If I add 0 to 0, it's still 0. I add 1 to 1, it's 2, but binary, it would be only 0. So the first class would have this evaluate to 0. The second one would evaluate this to 1, right? 1 plus 0 or 0 plus 1, they all evaluate to 1, okay? So in order to evaluate this function, if you use a classical computer, definitely you need to know the 2 values, f of 0 and f of 1. But interestingly, David Deutsch found that for quantum computer, we only need one use of the function. So that's the goal of this algorithm that I'm going to describe, how we can just use one evaluation of the function to achieve this. Any question on the setup? Okay, so the goal is to tell which class of the function is. So to do that, it's useful to introduce a trick. It's called phase kickback. So this is the rule that's given to us. So you can write as x tensor product b goes to x tensor product f of x plus b. For b, we can send in a special state 0 minus 1. If you want to be rigorous, you should divide it by square root 2. You can evaluate according to this rule. This rule is the unitary, the second rule, but it's already given to us. Let's just apply that. X times 0 is mapped to x times f of x plus 0. So that's f of x. If it's 1, this is f of x plus 1. Okay, and it's minus here. So this is really just using linearity, and there's a superposition, but basically just the unitary. And there is an interesting fact that I can simplify and say that this actually is equal to minus 1 raised to f of x times the state that I sent in. I mean, you can verify, for example, if f of x is 0, then this is 1, right? And that's 0, and 0 plus 1 would be 1. So that's the case. If f of x is 1, then this is 1. And this is 1 plus 1 equal to 0. That means it's 1 minus 0, so there should be a minus sign. And this basically take into account that minus sign. Okay, so you may require some time to do this, to think about this. It's called phase kickback, and I think I have an exercise for you to do in your homework. So the upshot is that this phase kickback telling us if we send a fixed state, I can rewrite this as minus sign of the function value acting times this x state. But because the second state is always the same, so I can just forget about it. If I only send the minus state here, then I can just keep this rule, right? So the unitary rule that I have is simplified to this rule. Okay, so we just need to remember this rule. So then we apply that, right? So I say that 0 is applied to minus 1 raised to f of 0. 1 is applied this action, right? So this is the phase kickback that I just used. So let's see how it goes. We know if it's constant. If it's constant, that's the same. So f of 1 is going to be equal to f of 0. But if it's balanced, meaning that they have different sign, right? They have a different sign. So this could be 0, 1, and then this would be a different sign. So that sign is reflected here. But if you compare the two, they are really different. It's the plus and minus basis. Remember, we have the Bloch sphere. This is up, down, and this is plus and minus. That means we can perform a measurement in that basis. If we measure and we obtain the plus state, we know it's a constant. And if we measure and obtain the minus state, we know it's balanced. Okay, so and then we only need to use one evaluation of the circuit. Okay, so let me just remind you the plus minus are really just 0 plus minus 1. Okay. In terms of interpretation, Deutsch interpret that the quantum computer actually explore a parallel universe. One is doing one part and the other doing the other. And when they bring back the result together to do some interference, then you know the answer. Okay, but this is also is a first hint that quantum computer can be more powerful than classical computer. Okay, so I want to comment on, so I mentioned that I have to measure in 0 and -1 base, so plus and -1 basis. But usually, and also I need to prepare these plus minus base states. But usually qubit, like in many quantum computers, they are initialized to 0, and the measurement is only in 0, 1 basis. So how do we perform initialization in the plus and -1? How do we measure in this basis? The answer is the Hardeman gate for the basis change. So you can use X gate to flip 0 to 1, and you can use Hardeman gate to flip 0, 1 to plus and minus. So if you have plus here, you can actually use a Hardeman gate to flip to 0 and 1 and measure in the 0, 1 basis. So in terms of the circuit, this is the implementation. If you start with 0, you want to prepare a minus state, you first flip this to 1, and Hardeman gate will take you to minus. So this block basically is a minus, and this block is basically plus. And this block is measuring plus and minus basis. Okay, so that seems a lot, but if you really just use the rule, right? So we only use unitary. We only use unitary rule here. And we simplify the rule to be a phase kickback. And then we use measurement. Then we achieve the goal that we can determine which category the function is, right? So I'm using only unitary and measurement. Okay, so this is the time I do a poll, and then we end the lecture. Then we just launch the poll. So which of the following is correct? First, entanglement require more than 1 qubit. Second, CNOT on any qubit will always create entanglement. Third, phase kickback in the algorithm require the input of the second register to be in the plus state. Hardeman gate turns 0 to minus. Which one is the correct answer? Let's take another 10 seconds. Okay, I'm revealing the poll and then tell you what is the correct answer. So the correct answer is entanglement require more than 1 qubit. CNOT on any 2 qubit gate will always, what is wrong is always. If you send in a 0, 0 state, it will have no effect. Phase kickback, you require the state of the second register to be, so here is the second register to be -1. Hardeman turns 0 to plus and 1 to minus. Okay, so maybe I stop sharing here. And any questions? There are a lot of material, but the nice thing about the online is that this is recorded, and you can maybe go back and review the part that you don't understand very well. But any questions?
Professor, can we go to the?
Can you speak louder?
Can we go to the algorithm slide? The page of the algorithm.
Okay, yeah. Since we already over the 4 o'clock limit, if you have other class to attend, feel free to leave the Zoom. But let me go back to my slide. Wait. Okay. algorithm slide. Okay, here.
Maybe one slide.
One slide before.
There was
Right, let me.
vector of x.
This one.
Yes, yes. Are the rows of x and b equivalent, or x is variable and b is constant?
Say that again.
Are the rows of x and b equivalent?
X and B, you mean the two line?
Yes.
So it's one, you're sending in one qubit that is in the state B, so X here. There's a second qubit comes in the state B. So there are two different qubits. So like what we have previously, like here, there are two qubits, right? In this case, I'm using the same input, but here I do a Hadamard to flip to the plus, and then I do the so-called CNOT gate, right? So here I'm doing something similar. So I'm sending x is arbitrary. It could be 0, it could be 1, it could be 0 plus 1, it could be any valid quantum state. B can be anything. So here we take advantage of sending the 0 minus 1 state in this register. Okay, and we use this rule, but we simplify because if we send in the special state 0 minus 1 in the second register, it does not change. So that means when we analyze the circuit, it's just useful just to look at the effect on the first qubit, but because the second qubit does not change. So this is a special state. Does that answer your question?
Yes, thank you.
Okay.
Can we go to the page with a sphere?
Page with what?
Sphere. With a sphere, the cat of up and down and plus
Okay.
and minus.
Like this.
Yes. What is the meaning of the cat, the plus and minus inside?
Oh, okay. So maybe I should go back to the earlier one. When we derive the sphere, right? So we really derive this sphere. Yeah. So the 0 is up, 1 is down. The plus is in the x direction, right? Minus in the opposite x direction. So in this x, I have a coordinate where theta is pi over 2, phi is 0. So this means my alpha is square root 2, beta is square root 2, right? The minus x part has a phi equal to pi, right? So it has the same alpha, but beta is minus. So that's why I label plus as 0 plus 1 and minus with a minus sign. Okay? Makes sense?
Yes, but I don't understand why we have a phi here. Since we already have the alpha square plus beta square equals to 1.
Yeah, but it's complex. It can be a complex number. Alpha and beta are complex in general. Okay. And here I do not have a phase because it's overall. I just extract the overall right? I could put an overall face into here. Let's say chi, then I can also add it here. But I can just remove that overall. Okay.
Thank you.
Sure. Any other questions? Okay, if not, I would start the recording and end the class. I'll see you next Monday.